In the process of teaching you something new today, I'm also going to do a little bit of review. Way back when in the beginning of chapter 4, we started looking at functions and we defined what an antiderivative is, and we talked about the idea that it's the area under the curve. And so we did that a bunch of different ways. We started by approximating the area under the curve. So we're actually going backwards from what we did. So it might be a little confusing when you look at the assignment sheet. We're going all the way back to day 67, even though we've done 68, 69, 70. I think we're on like day 73 or something like that. But this is something we didn't have time to cover before the exam, so it's important that we do it now. But, okay, back on track. So we did things like we did left hand, right hand, circumscribed and inscribed rectangles to approximate the area under the curve. So if you recall, we, in this particular case, I'm going to go from 3 to 9, and I have a width of 2. So refreshing some terminology here for those of you that may have forgotten, b minus a over n equals delta x. What's b? Good. What's a? Yeah. So ending point, starting point, n?
The number of
divisions. Yeah, number of rectangles, whatever you want to call it. And delta x? The width. In this case, what's delta x? 2. That wasn't meant to be that challenging of a question. It's just 2 squares. Or from 3 to 5 would be 2. Oh, this might not go well. Okay, so we got delta. Oh, by the way, what did Riemann do different from this? What was his big contribution? Say again, I'm sorry.
Did he change the size of the space?
Yeah, he didn't mandate that all of the rectangles be the same width. You could change them, and then we did some limits and all that other gunk. We're just going to worry about some nice, pretty delta x, and in this case, we have a delta x of 2. Okay, so let's suppose in a lovely shade of blue, we decide to do right-hand rectangles. If you'll recall, we start in this first region. We go up the right-hand side of the rectangle, hit the function, come across, and bingo, I've got my first rectangle. Good approximation, bad approximation? Bad. A lot of wasted space there.
Yes.
And you all see the wasted space, yes? Okay. Second region, same thing. Go up the right-hand side, hit the function, come across. Here's our rectangle. And then lastly, up the right-hand side, come across. Rectangle. Okay. The leftmost rectangle, is that circumscribed or inscribed? Circumscribed, because it's above the graph. The other two are inscribed, okay? And like we said, we've got a bunch of wasted space there, so this is not a very good approximation. Wasted space here, wasted space here, and wasted space there. How could I make my answer more accurate using rectangles?
Make them smaller.
Good. Make the rectangles smaller or increase the number of rectangles. It's the same result. And then you'll recall we talked about shrinking the width of the rectangles down to 0. So you have an infinite number of them, which also sounds like something called the limit. Okay, so that's all review. We're good to go? Yes? Okay, new stuff now. If I get rid of all this mess and start with the same idea, as the title implies, instead of oh, wait, I forgot something. Hold on. We never talked about this, but I just did right-hand rectangles. You should be able to do a left-hand rectangle here. What we haven't talked about is, what do you think a midpoint rectangle is? Huh?
Is it a rectangle where the line drawn is the middle?
Perfect. It's not very common, but I thought it was important that you understand what it is. So in other words, if I'm going from 3 to 5, I'd go at the midpoint, which would be 4, go up, hit the graph. In this case, you got to go left and right. Okay, the other one, go up 6, hit the graph, come across, and then the last one would be 8, and we get that. So now there's three types of well, there's five actually. Left hand, right hand, midpoint, circumscribed, inscribed. As far as the left hand, right hand, and midpoint goes, none of those is going to be the most accurate answer. It depends on the shape of the curve. It depends on the concavity. Is it increasing? Is it decreasing? But again, I just thought it would be important that you see what a midpoint rectangle is so that you didn't have to figure it out on your own. Okay. Now, trapezoid rule. Well, let's get a more accurate answer. And we can get a more accurate answer by just creating trapezoids. This one requires 3 of them. You'll see that the amount of wasted space is much smaller, so it's going to give me a more accurate answer. And for the most part, the trapezoid rule will give you a more accurate answer than any of the rectangles. Okay, little review from geometry. What's the area of a trapezoid? Page? 1/2.
Oh, we side one.
There's a B1 plus B2 in there. H. Good. Okay. That's from geometry. Now, relate that to calculus. In my picture over here, what's H?
Oh.
2. Or also, in general terms, delta X. What's B1 in this case? Let's talk about the green trapezoid. What would B1 be? Don't give me a numerical value, give me an expression for it. How would I find it?
The starting point
Keep going.
plus the ending point.
No. Not quite. Tom?
X equals 3. But for the on the picture, plug into the graph.
Yeah, what's the way to say that?
F of 3.
Thank you. F of 3. Okay, the y value at 3. And for the green, the B2 would be F of 5. Okay, so that's the area of the green trapezoid. Before I go any further, is everybody good with that? Okay, so B1 becomes the height of the base of the trapezoid, and notice the trapezoid is turned on its side. B2 is the height of the trapezoid at 5, and then we can continue. What is that, pink, purple? What color would you call that? What color is the middle one? Pink? All right, we'll go with pink. 1/2 delta X times, what's B1? F of 5 plus B2? F of 7. And then the last one, the area of the yellow one, 1/2 delta X times B1?
F of 9 plus F of 7.
Yeah, F of 7 plus F of 9. Good. Add them up, you're done. Oh, real quick, how would I find F of 3, F of 5, F of 7, and F of 9? Yeah, you need the equation to plug it in, and then, I mean, that's a cubic. I forget what the formula was that I used to draw the picture, but plug and chug and get the y values of those functions. Anything tricky about that? Good. We're done. That's it. Nice, easy trapezoid rule today. Okay, this will wrap up chapter 4, and then we'll start tomorrow with moving on to chapter 5. Again, the assignment sheet on the calendar is a little wonky. It says day 67. The page and the numbers are correct. The day is off a little bit because, again, we were supposed to do this a while ago.